All right. So yesterday we talked pretty much strictly about um, things that came in intervals of one or two or three standard deviations. There was one problem on the assignment that I kind of gave you that was in between two standard deviations that you probably weren't able to get right. I kind of put that on there on purpose to sort of lead you into today's stuff, to have you get a feel for. Okay, so I know what I can do when it's one or two, or well, one or two or three standard deviations. But what happens when it falls in between certain numbers? What does that mean? And so that's what we're going to get into actually today and tomorrow. So that one question, like I said, that was on the would have been yesterday's. What was that? 11.4a. If you missed it, no problem. I did it on purpose because I wanted to see like what you might do with it. But we'll see more about it here over the next 2 days. So let's read this question. We're going to learn about something called a z-score today. So let's read this, and then we'll define what a z-score is. So it says Ella and Alicia, I think, yeah, Alicia, yeah, are comparing scores in their college entrance exams. Ella's SAT score is 1380, which is a really good score. It's out of 1600. Alicia's ACT score was 32. Okay. So ACT is out of 36, by the way, if you're curious. The mean SAT score is 1,000, and the standard deviation is 200. The mean ACT score is 21, with standard deviation of 5. So the question is, who has the better score? Now, what you don't want to do here is you don't want to just do it by percentage. Neither of these are technically percentage-based tests. Like, so 1380 out of 1600 versus 32 out of 36. These are tests that are scored based off of how everybody else does. So what that means actually is a 1600 one year might be different than a 1600 another year. Like some years a 1600 is actually a perfect score. But then some years people get a 1600 and they missed one question. Or some years they did it and they get missed two questions. They scale it depending on the difficulty of the test. They actually average it all, and then they set out the scores based off that. Which is kind of interesting, but that is how most really large standardized tests are scored. So anyway, the case here is they're giving you the means and the standard deviations for both of these, and they're basically saying based off that information, who's actually doing better. So what we want to do here is we're going to use a thing called a z-score, which is a way to compare how many standard deviations above the mean two different sets of data are. So I'm going to write it down here, and then we'll kind of just conceptually talk about it too. So a z-score is calculated by doing x minus x bar over the standard deviation. And you should know most of these, this is standard deviation. This is the mean. We've seen those before. The x is just the one data point you know. In this point, it's going to be each of the girls' scores, but it's whatever number you're given. So it's basically your given number minus the mean divided by the standard deviation. And this is going to give what's called the z-score. And the z-score, if you want to define it here, is the number of standard deviations that a single value, sorry, you can't see that, is above or below the mean. So what this is going to tell us, this is going to give us an individual z-score for each person, and then based off who has the higher z-score is going to have the more impressive performance because they were that many standard deviations above the mean versus the other person was less. So it's actually the concept of this kind of makes sense. You're seeing who did better in relation to the standard deviations above the mean because that's showing that they had a greater performance above the average. Okay. So with that said, let's go ahead and calculate these. So my girl Ella here, she took the SAT. So when we're calculating her z-score, her score was the 1380, and the average on the SAT was 1,000, and the standard deviation 200. Okay, so we calculate that. That's going to be 380 over 200, and these are almost always going to give you a decimal value. So 1.9. So she is 1.9 standard deviations above the mean. In other words, she's almost 2 standard deviations from the average. All right, and then our other girl here, Alicia. I don't know what I'm writing there. There we go. Her z-score, she scored a 32 on the ACT, which has an average of 21. Moving on over here, and the standard deviation from up there was 5. Okay, it's the same thing. Let's calculate this. That's going to be 11 over 5, which is going to be 2.2. And so at this point, this kind of answers our question because whoever has the higher z-score means they're they're more standard deviations above the mean than the other person. So in this case, we could say that Alicia's score is statistically better. Okay? And this is exactly how colleges would do this. Because colleges take both SAT and ACT, at least most colleges do. And what they do is they normalize their data. And actually that phrase right there, normalizing data, is exactly because it's normal data. They look at the two and they compare the z-scores, and it allows them to decide, this girl did better. We're going to admit her. Let's say both these people were right on the edge. They only got one spot open. They're going to pick this one because it just happens to have a better score. That's a little simplified version of that, but that is exactly how they could compare two people who took a different test. And so that's pretty cool. Now, you can also kind of just do this conceptually. Like if I was looking at this, I would look at it and say, well, all right, so what's two standard deviations above this? That'd be 200 and 200, so it'd be 1,400. So I would look at that and be like, ooh, she was almost 2 standard deviations. And then I would look at this and be like, okay, if standard deviation's 5, so 5 and 5 would be 10. So 31 would be 2 standard deviations. I can see right away, oh yeah, she's more than 2 standard deviations above. So you can actually kind of even just do it by sort of looking at it and comparing the numbers as well, which can be valuable. But in most cases, we're going to want to just calculate the z-scores exactly so we can compare the two numbers. Okay? So yeah, that's the main concept with the z-score. Now, here's one that's a little different. This is going to kind of solve for some values. So here we've got Keith. It says Keith's score in the card game Hearts is 91. And Bruce's score in some other game called 5 Crowns, which I've never heard of, is 245. Both players had a z-score of 2.9. The standard deviation in Hearts was 6, and the standard deviation in 5 Crowns was 23. Compare the means of the games. So we're going to have to do two separate little calculations here. We're going to do a calculation for Hearts and a calculation for 5 Crowns. And basically for each one of them, we're going to do a z-score where we're going to put in everything we know, except the mean is the part we're not going to know. So they said z-score was 2.9, and that's true for both scenarios. So I'm just taking my z-score formula here. And then let's just do the Hearts one first. So we're going to take the data point, which was Keith's score of 91. We're going to subtract the mean that we don't know. And we're going to put it over the standard deviation, which we were told was 6. And at this point, all we need to do now is solve this equation. So if we solve this, you're going to use kind of your basic cross-multiply type move here. So the 6 times the 2.9, we get 17.4 equal to 91 minus x, x bar technically. Add the x bar over and subtract the 17.4. So when you do that, 91 minus the 17.4 is 73.6. So that is the average for Hearts. That's the mean, the average score in a game of Hearts. And we would just do the same thing over here for the 5 Crowns game. His score that Bruce got was 245. We're going to subtract the unknown mean over the standard deviation of 23. Same process, just different numbers. So we'll cross multiply the 23 and the 2.9. Gets a 66.7 equal to the 245 minus x bar. And just like the last problem, add the x bar over, subtract the 66.7 from the 245. And I get 178.3. And there we go. So this is just a problem where you're using the formula to solve for a specific variable versus other problems where you'll find the z-score and use that to analyze who had the better performance. We're going to see a little bit of both these in the assignment today. And that's going to be pretty much it. So we'll finish this section tomorrow. If you notice, the notes are done, but I'm going to show you one more skill tomorrow, and we'll do the lesson summary to kind of wrap it all up. And that'll be good for 11-4.